The broadcast is now starting. All attendees are in listen-only mode.
Good evening, Joe. Can you hear me?
Yep, sound loud and clear, Bryce.
Perfect.
Excellent. All right, we'll get started in about 2 minutes. All right, good evening, everybody. It's 7 o'clock, so we are going to go ahead and get started with tonight's webinar, which is Weather 202, also known as forecasting. So we're assuming everybody, Bryce, passed Weather 101, so they're allowed to take this course as well. We will be recording this. It'll be on our YouTube channel a little bit later, so you can always go back and take a look or review Weather 101 if you want, which is some basic weather. But we're going to get into a little bit about forecasting tonight. Which I know we actually had a lot of people sign up, which is great. So go ahead and use the chat box as we go through. Bryce and I will try and answer questions as we go along if we end up getting a lot of them, but we'll also answer some at the end. And again, this will be recorded, so it will be on our YouTube channel a little bit later. And as always, feel free to send me your feedback or if you think of any questions a little bit later. And we will follow this up with a weather briefing, so we'll kind of put everything into practice and give you kind of a real-time example on forecasting. So a reminder, we have some upcoming webinars here before Thanksgiving. We moved one to a Monday night, which we don't do too much, but we want to fit it in before the holidays begin. So we're going to review the late October nor'easter next Monday. That will be at 7 p.m. Frank Nocera, I believe, is joining me for that. And then next Thursday, that will be November 18th, Rob Megny is going to be with us to give the winter outlook for 2021 to 22. The NOAA outlook is out, and I'll show that at the end. But Rob's going to talk a little bit about some of the factors that have gone into this year's outlook and maybe localize it a little bit here for us in southern New England. So stay tuned for that. And again, you can email me if you want to get on our notification list. We've got over 35 people now, I think, Bryce. And when we add a webinar to our webpage there, I also send a BCC email and just let you know that we have a new webinar scheduled so you can sign up for it. So feel free to drop me an email and we can add you to the list.
I want to welcome everybody to tonight's discussion. And again, just to reiterate, if you have questions for me, throw them in there and I'll try to answer some as we go. And then at the end, we'll follow up. And finally, just wanted to reiterate kind of what Joe said. If you come across some things that you don't understand that we kind of mentioned here that we may not explain as much, it's probably, or more than likely, it's something that we've covered in our previous more basic weather class called Weather 101, and that is on our YouTube page. So in case you haven't seen that, you can, after we're done here tonight, you can go to our YouTube page and watch that, and that's more of a intro basics of weather. This is going to be a little bit more technical than the average Joe typically ever hears about. So if you're here, you're probably kind of a weather weenie like we are, and we just love this kind of stuff and the science of it. And so we're going to dig a little bit more into that tonight. But first, before we start into the kind of science that goes into forecasting nowadays, I wanted to start back with a look at how forecasting has evolved over the decades and centuries that we've had any sort of weather forecasting. So a little bit into the history of forecasting. The first weather forecast were basically relying only on observations that could be made at that specific location, just because the lack of communication, easy communication from long distances made it nearly impossible, and the lack of technology as far as even instruments to observe the weather. So very rudimentary in the beginning, observations of things like the sky cover, winds, temperatures, conditions, and then kind of combining that with a person's knowledge of whatever the local climate history. It provided a limited predictability, very limited. Then, in a little bit of an upgrade, was in the 1800s, the invention of the telegraph is something that allowed observations to be relayed from far off locations that were able to kind of get an idea of what's going on, maybe upwind of us or downwind. And these let us create what's called synoptic weather charts. And so on the next slide, you'll see kind of an example of how little we had to work with back then. This is a really cool map that is was from the War Department. So you see the top War Department weather map from 1871, the New Year's Day, 1871. And you can see these are all the weather observations that we had to work with. If you looked at an observation website nowadays, there's thousands and thousands and thousands across the country, and all of these you just see a handful, and they're all east of the Rockies. So you can see how just kind of rudimentary our observation network was, and they're very far off. And as we were able to start transmitting data long distances, that helped us to kind of assimilate all this together. So then stepping ahead again into the 1900s, the 1920s specifically, that is when we made a big leap with a Norwegian scientist, Wilhelm Jerknes. I'm not positive I'm saying that right, but he came up with the polar front theory. And this is kind of one of the foundational theories of meteorology. And this describes the large-scale movement of different air masses. And what this did was it allowed for a much better understanding of just the atmospheric circulation and systems that we know today as cyclones, anticyclones, and how these systems work together to form precipitation. Stepping ahead, looking back a little bit about the actual observation, how observation also moved ahead. In August of 1894, we had our first very rudimentary, what you would call a radiosonde or an upper air flight. We use balloons now, but this was actually done with a kite. And also, it's a local historical landmark because this was at our very own Blue Hill Observatory in Massachusetts, southeast Massachusetts. So very interesting factoid there. So a series of 5 kites was made by William Eddy, a New York journalist, lifted a special lightweight thermograph constructed by Ferguson to a height of 1,400 feet above the ground at the Blue Hill. And so this was the very beginning of what are known as soundings that are now taken worldwide. And these send us back pressure, temperature, humidity, and wind speed. And we'll talk about that later. So on to the 1930s. So these radiosondes, which is what you see in the bottom right here, eventually we realized that we could get them higher if we attach them to balloons. So we attached them to balloons, and these allowed for observations all the way through the atmosphere. So no longer are we only getting stuff just from the surface. And so this was revolutionary because it extended and refined the forecasting concepts from this polar front theory by revealing things in the upper atmosphere like the jet stream, which is a ubiquitous term now, but back then was unknown until we sampled it. All right, and so then we get into the modern era of forecasting. I say modern is a relative term, but the modern forecasting techniques that we use today were propelled by the work of an American meteorologist named Jules Charney, and he developed what is known as numerical weather prediction. And so this basically just means weather phenomenon being predicted by solving equations that govern the behavior of the atmosphere. And that's him on the top right there. So we're going to get into, what exactly that numerical weather prediction looks like nowadays later. But for now, we'll move on from kind of the history of forecasting and start on types of forecasting techniques and methods. So kind of what a general rule of thumb and a ground thought about forecasting the weather that meteorologist has is weather is going to stay the same from day to day until the pattern is broken. So the pattern is only going to change when there is some new influence that is there to break the pattern. And as meteorologists, we term this persistence. Basically, if you're saying a forecast for a future weather condition will be the same as it is right now, that's known as persistence. So if we're still going to be high pressure tomorrow like we were today, we may have a very similar forecast known as persistence. Another method is the climatology method. This is based on weather statistics and averages that we gather over multiple years. So say, oh, well, the average temperature on January 5th is 30 degrees, high temperature is 30 degrees. So we're going to make a forecast and say it's probably going to be 30 degrees on January 5th. So very rudimentary and not super scientifically accurate, but statistically, you have a better chance of being right than if you were totally to guess a number out of the air. So that would be climatology based on averages. And then we have what's known as analog. This is something that we use today, and there are some interesting websites very useful for finding analogs. But this is basically finding a day in the past that had weather very similar to what is currently forecast. So say there's a low pressure system over the Great Lakes that the upper air pattern is such that it looks very similar to how it did on a day back in 1978. We can see what happened in the days after that in the 70s and think maybe that would be something that's similar to what would happen in the next couple of days. That is finding an analog to our current situation. And then another method that we utilize is the trend method. So basically, you're just determining the speed and direction of the movement of different things like fronts, highs and lows, areas of clouds and precipitation, and just using that to predict where you expect those features to be at some future time. So you're basically just saying, okay, it's moving 50 miles an hour now. We're going to assume it's going to continue to move 50 miles an hour, and we can extrapolate down over the next 24 or 48 hours and assume that the front or the low or what have you is going to be in this location in 24 hours from now. So more, again, rudimentary, but it is helpful. All right, and then we get to the biggest part of weather forecasting in the modern era, and that is the numerical weather prediction that I talked about. So today, that's all done by these supercomputers that run hundreds of thousands of equations a minute. And so these supercomputers run various forecast models that help us as meteorologists to make predictions based on multiple conditions in the atmosphere, like temperature, wind, speed, high and low pressure systems, et cetera. And you can see an example of kind of some of that model output here. It's known as a spaghetti plot showing what the track of a potential tropical system. And we'll get into the nitty-gritty of numerical weather prediction at a later slide. All right, so moving on from different methods to the forecast process. So the forecast process has to start with observation and then analysis. So before any forecast can be made, we as meteorologists have to first understand what is happening now, what the conditions are now, and what is producing them. So this is done by looking at a huge amount of data, observational data that can include things like satellite imagery, radar data, ASOS systems, or basically systems on the ground at airports and such, weather balloon data, aircraft observations, river gauges, all that stuff is a form of observation that is used to go into the forecast. So the forecast process starts with observation. These are all examples of different observation that we'll talk about. All right, so the ASOS system I mentioned is one of the most widely recognized observation systems, and this stands for Automated Surface Observation Station. And you see a picture of it there on the left. This is a pretty standard example of what you would see at these are most often located at airports. So if you see these out on the airfield, that is a weather observing station. And they're plotted with these little graphs, a map like you see here, and I'm gonna break down what all these numbers mean later, but these are all different ASOS stations that are showing temperature, dew point, wind speed, direction, weather, all sorts of stuff that you can glean from this. Another one of the most recognized by your everyday person at home is radar, because you'll see this on their phones, on their TVs. And so we'll talk a little bit about what this is and how it works. Even I'm not going to spend too much time on it because we've covered this in several previous webinars. But in general, let's go on to the next slide, and we'll show you how it works a little bit. Basically, there's a big dish inside a radar dome, which you'll see here in a minute, and it's rotating and sending out bursts of a radio signal called a pulse. And this pulse will then bounce off of anything in the atmosphere, like a raindrop, hailstone, what have you, and come back to the antenna. And so it's listening for a return signal. And these bursts are very, very short, so it is listening most of the time. And so when it does hear back, then it paints an image on a map of where the rain or hail or whatever it is, snow, is in the atmosphere, as you see on the right. And it's ever tilting upward. Now we have a huge network of these across the country, and you see it all here. This is a map showing all the black dots are radars, and this is showing the coverage map. So you can see the eastern half of the country is most well covered. You can see where we have lots of terrain out west, there where the Rockies and whatnot are. We have some gaps, obviously, because the radar beam runs into mountains. But the vast majority of the country is covered by radar coverage. This is what ours looks like at the office, and you can see just how big it is there with an ET at my old office standing next to it inside. And you can see it rotating here on the next slide. You can see how it works inside. So in that big volleyball-looking thing, it's a big dish. All right. So the next thing I'll talk about, the way we get observations, is what used to be done by kite, we saw earlier, is now done by balloon. And these are done twice a day, every day, at about 92-ish sites across the country. So not every office does it. And I'll show a map of that here soon, I think. So this little package will go up to about 100,000 feet. So almost into, it seems like it's almost into outer space. I think we have a picture later. It goes very high, sending back data. Oh, and this is just a video of me doing a balloon launch during a windstorm back in 2015 at one of my old office in Spokane, and you can see it get caught in an eddy, and then it eventually catches that wind and shoots off nearly horizontally and almost into the power line. So, not every balloon launch is boring. Something can be pretty exciting. But this did send back valuable data. So this is a picture from a GoPro that was attached to a weather balloon right before it popped. So you can see it goes very high, about 100,000 feet, and each flight lasts about an hour, 45 minutes. And then there's a parachute to catch it as it floats back down to the surface once the balloon pops. This is what's known as a Skew-T Log P Diagram. This is the data this is all the data that we get from the radio sonde. And I'm not going to go over how exactly to read this, but the red line is temperature, the green line is dew point. So where they touch, that's where we can know there are clouds, and where they're farther apart, that's where the drier air is. And you can see the wind barbs on the right show the different wind speeds and directions as you go up in the atmosphere. These are all of our radar site, or our upper air sites. Rest in peace to our Chatham site, which is in the process of being replaced. Erosion almost got it. We had to demolish it because it was about to fall into the sea if we left it there for too long. So we are going to be finding a new site for it, as soon as we can. All right, moving on to satellite data, a very big component of a forecaster's toolbox. You can see we have what's known as a polar orbiting satellite on the left, and that circles the poles, you guessed it, or a geostationary satellite. This is a satellite that stays in the same place over one spot on Earth and orbits with it. So these are just some examples of what's known as infrared satellite data on the left. That's showing the temperature of the cloud tops. The colder the temperature, the taller the clouds are. And on the right, you see water vapor imagery. The greens and whites are lots of moisture, while the blues and yellows are very dry air. So that's just a very small sample of what we can get from satellite data. Oh, this was a cool shot, just because you can see, we can even see at night, during the nighttime, we have a fog product, and you can see that the dark or the light blue is kind of low clouds, and sometimes it can be used to show fog. And then you can see the city centers underneath, and some higher clouds up to the north. So just even at night, even when we can't see, these instruments let us be able to see what the clouds are doing out there. So it's pretty cool. All right, so that's the observation part. Now I mentioned analysis. What does that mean? So after we have all the observations together, we can start analyzing what's going on. And so on this slide, I wanted to highlight something that's known as hand analysis. So this is a technique that is still very prevalent among meteorologists today, especially during active weather and really impactful events. This can really help. So even though we have very powerful computers nowadays that can analyze maps, there's really no substitute for drawing on a weather map by hand and really getting an idea of where these features are set up and what is happening right now. Without knowing the intricate details of what's happening now, a forecast can suffer, because if you're starting from the wrong initialization point, we call it, at the beginning, then that's just going to throw your whole forecast off the further you go, more and more the further you go out into the future. So this can help you track the evolution of fronts. So say you do a surface or a hand analysis every 3 hours, it can help you track the process or progress of things like fronts, jet stream, cyclones, anticyclones, and use this information for pattern recognition. Basically, kind of like the analog I talked about, thinking of when have we seen this before? When have I, as a forecaster, in my experience, I have seen this situation play out similar before, and it can help me remember what happened in that situation, and know what might happen now. So with hand analysis, often people will do a surface analysis. So this is basically plotting those ASOS observations that I showed earlier, and they look like this on the right, on the bottom right. There's all sorts of data we can get from here, and I'll start with the wind. This little barb that sticks off to the upper top left is a wind barb, and it not only tells us the direction, so the wind is coming from the northwest here, or the northwest, so that whichever direction the barb is facing, that's the direction the wind is coming from. And then these little ticks, the long tick is 10 knots, and the short tick is 5 knots. And if you see a triangle, that's 50 knots. And then you have the temperature on the upper left, the dew point on the bottom left. The sky cover is shown by whether or not or how much this circle is filled in. So right now we'd have clear skies because it's not filled in. And then we have sea level pressure on the bottom or the top right. And not every station shows this, but some will show the pressure trend. And if that's the case, it'll be on the right here. You say that the pressure has decreased by 6 millibars in the last hour. And on the left-hand side, it's a very useful thing is the weather symbol. It's symbol for what is happening right now as far as the weather. And this chart on the left shows you some of the most common weather symbols and how to interpret them. So the rain is going to depend on how many dots there are. It shows how heavy or light the rain is. And snow, you can see there, thunder, drizzle, freezing rain. There's symbols for all sorts of things that we won't get into every single one, but that's just an example of some of the most common ones. All right, so what to look for at the surface. So if you're trying to, you're at home and you either print off a surface observation map or you're just looking at it online, what kind of thing can we identify? So most often you're looking for cyclones, so the low pressures and high pressures, and their fronts and boundaries. So things like cold fronts with the blue triangles, warm fronts with the red circles, stationary fronts, which is a mix of the two. The purple is shown by, or shows what's known as an occluded front, troughs or trough axes, which I'll talk about, outflow boundaries, dry lines, things we talked about in Severe Weather 101, and ridge axis. All these things in examples you can see on the right here of the dry line, the warm front, cold front, some ridges and troughs, lots of good stuff. All right, so that's the surface. So now it gets a little bit more complicated as we go up in the atmosphere. So for upper air, so what we call upper air charts. So this is when we're analyzing surfaces that are higher than the ground level. These are called upper air charts, and we define them by their pressure level, say 850 millibars all the way up to 200 millibars. So for these upper air charts, they are constructed at a level of constant pressure. And the relation of pressure is plotted in terms of what's known as geopotential heights and the location. So this is basically the location from an upper air sounding in the vertical component where that pressure level is. So on a sounding, we can see what height, say 5,000 feet, the 850 millibar level was. And so that's how it's a little bit obtuse, abstract, but just know that this is how we're going to talk about different heights. We're going to be talking about them in pressure levels. And as you go up in height, the pressure goes down, as we talked about in Weather 101. So the higher we go, the lower the pressure is going to be. All right, so now we're getting into the upper level. So we need to talk about what we're going to be identifying most often, and that's going to be things known as short waves and long waves, or troughs and ridges. So these waves, these waves you see here with the gray lines, they form things known as a trough, which is delineated by this dashed line here. But you can think of them like kind of like waves in the ocean, and ridges where they crest over here where you see the jagged line. And so these troughs can also be known as a long wave. We also have short waves, which are kind of smaller kinks in the height contours. And so we'll see examples of some of these in the coming slides, but just so you know kind of the terms what we're using, long waves, short waves are another term for things known as troughs. All right, next slide. So some of the things to look for, some of the patterns to look for when we're looking at upper air charts. So we'll start with, these are some of them, I just threw in some of the most common patterns that we see when we're forecasting. First, we'll go talk about an open wave. This is just your classic, trough, ridge, trough pattern. Pretty typical, nothing super special about it. We have storm systems moving across the country. Then we'll have something known as a positively tilted trough. This is when the trough is tilted from the bottom left to the top right looking at the map, from southwest to northeast. The trough axis is slanted that way. And these are more associated with the less severe storms or just rain, not as severe. Whereas the negatively tilted trough, when we see a negatively tilted trough where it's the opposite, it's the trough axis is going from the northwest to the southeast. That is indicative of more severe storms ahead of that trough as it moves across the country. So we don't like to see negatively tilted troughs. And then we have what's known as zonal flow, which is when there isn't really much of a trough or axis pattern across the whole country at all. Meridional would be where it's very wavy, and zonal would be where it's very flat. And so you kind of often have kind of cool to the north and mild to the south along a pretty straight line. Then we have things called cutoff lows, and this is when a upper area of upper low pressure, or a low pressure in the upper atmosphere, I should say, it kind of escapes the steering of the jet stream, and it gets cut off. That's why it's called a cutoff low. And so it can languish there and just sit there and spin and spin and and cause lingering cloud cover and rainfall for long periods of time until eventually it gets absorbed back into the jet stream, into the upper level flow, and it gets kicked out to the east. Then we have blocking highs, which are responsible for a lot of our heat waves, especially when you talk about down south in the southwest. You can get what's known as a heat dome, and basically just a big area of high pressure that doesn't want to move. And so you have sinking air that's warming as it sinks, and it's causing a heat wave. Then we have an omega block. These are getting in the more obscure niche type of patterns, but an omega block is something that we'll see. This is named that because of the shape. It looks kind of like the omega symbol, and so you can see it occurs when you have a high pressure to the north and two low pressures on either side to the south, and it can kind of get blocked. It can block much movement from happening across the country. It kind of can be stagnant. Another block where we have not much movement is a Rex block, and this is where we have a large high pressure to the north and a low pressure right next to it to the south. And so these in tandem create what's known as a Rex block. So if you ever see those, you'll know what to call them. All right, so now that we're moving, we're gonna go layer by layer, and I'm gonna let Joe take it from here. Unless Joe, did we want to talk about any questions before you went on, or do we want to wait?
Yeah, no, we've just had a couple so far, but you can go ahead and monitor those in the chat if you want. And
okay.
There's not many, so we can even read them aloud afterwards too. But
sounds good.
I just figure we might get a lot of questions, so we'll keep an eye on the chat as I go along, Bryce. So all right, thanks a lot. So let's take a look at some of the different levels and kind of what we look at in each of the levels. So this is 850 millibars, and this is about near 5,000 feet. The level actually varies because we're looking at constant pressure, not constant height. So when it's colder in the wintertime, this level is lower than 5,000 feet. And in the summertime, when it's warmer, it's actually a little bit higher. But on average, it's about near 5,000 feet. So what we look at here is really moisture. This is our kind of our moisture feed into, let's use the winter time here, like a winter storm. So we're looking at things like relative humidity, maybe even precipitable water, but definitely looking at relative humidity at this level. And also, the wind speed, low-level jets are located at this level. So are we getting a low-level jet off the Atlantic, for example, to provide moisture into a winter storm? So, when we look at moisture, things like precipitable water, when we have an unstable air mass in the summertime, again, high instability, what we know as high CAPE, and high precipitable water tells us we get storms with lightning and flash flooding as well. So this is usually where we're looking at for moisture. If we don't have a lot of moisture at 850 millibars, whether it's severe weather or a winter storm, you're probably not going to get too much in the way of rain or snow. So this is one level you want to look at. And not just one level, you also want to look at layers. So typically, Bryce, I'll take a look at the levels here from 850 all the way up to 500 on a model and see what the moisture is. Make sure it's a deep layer of moisture and not shallow. But certainly at 850, that's kind of one thing we look at. Also look at things like, temperatures, cloud cover based on the moisture, again, low-level jets, pressure gradients, or are we getting warmer air moving in or colder air moving in? So if you followed our webinars on some of the event reviews, you've probably seen quite a bit of this, and feel free to go to the YouTube channel, check out some of the event reviews. We review a lot of the upper air features here too. So that's about 850 millibars. Now, going up a little bit higher now, we're at 700 millibars, which is around 10,000 feet. And as with 850 millibars, we're looking for moisture, but we're also looking for vertical motion. Do we have any lift? This is kind of the layer where you want to have the lift. And we used the term before omega, but we also use omega to represent vertical motion on these 700 millibar charts. So we're looking at wanting to have some sort of lift or strong omega to provide lift to generate rain or snow. And this trough and ridge pattern, you'll see it become more defined at 700 millibars and to about 500 millibars here on the right. Compared to some of the lower levels. You will see it, but it's more pronounced in this layer from 700 to 500 millibars. So I would say if you're looking at those two layers, take a look at moisture, take a look at vertical motion in that layer too. And this is also, again, it's a good level to search for cloud cover. troughs and ridges, looking at things like directional and speed, the wind shear when we talk about severe thunderstorms, and particularly those involving tornadoes. So again, take a look at some of our event reviews for severe weather. We go into that quite a bit. And then for the winter weather, we will use this to look at things like lift and moisture moving in as well. This is the level 700 millibars when we talk about the deformation zone, that inland heavy snow band associated with our nor'easters. That's at this level, 700 millibars. And then we go to 500 millibars, and this is, we call it the quintessential upper air chart. It's kind of where we start. I think, Bryce, when we took synoptic meteorology, everything was 500 millibars first. This is where you learn troughs and ridges and everything. And this is considered kind of the middle of the atmosphere, or I always call it kind of the steering level of the atmosphere. The highs and lows to near the surface are kind of steered by what happens here. So you're looking at anywhere about 16,000 to 20,000 feet on average. And as I mentioned, it's often used to grasp and understand the mean flow of the atmosphere. So those long waves and short waves that Bryce showed, typically we start here at 500 millibars. And you analyze different things, again, regions of saturation. You want deep moisture. So I would, look at the 850 to 500 millibar layer for moisture, probably for lift as well, although you can also look at 700 to 500 millibars. The wind speed is important, and something called vorticity, which is a measure of the spin of the atmosphere. And that's associated with these long wave and short wave troughs. So if we have a very strong, what's called a vortmax, then that provides extra spin, extra energy, and helps a low pressure system at the surface strengthen pretty quickly. And probably, in the wintertime, we'll look at these to become big winter storms. So here's a couple of examples. And again, this is a good level to search for your troughs and ridges, your jet streaks. You can see a good deep trough here in the Rockies, a little bit of a ridge here in the east. And this is a shortwave right here. Notice it's a smaller scale trough than what we have out on the west, which is a long wave trough. So that's how we define the two. And this is a hand analysis. Again, we do those too. Really helps grasp better understanding, looking at things like this is an upper low with a pretty good jet max at 500 millibars. And this was from a tornado event in May 31st, 1985. And this was the reason why, a cutoff low and a very strong jet max across the Great Lakes. And then we move up a little higher. Now we're getting up near the jet stream level. So 300 millibars is typically in the summertime because it's a little bit warmer. So this is going to be, a little bit, probably the area of stronger winds. And in the wintertime, we look a little bit more at like 200 millibars or so. But this is near the upper levels of the atmosphere. And again, primarily used to locate the jet stream. And that's essentially where it's 70 knots or greater, roughly, 80 miles per hour. And I'll show, I was usually showing the briefings too. We go through this jet stream level. I usually look around 250 millibars on average, but it can be anywhere in that 200 to 300 millibar layer. And the wind will almost always blow parallel to the contours at this level. So here's an example of a 300 millibar map. Again, similar to the other upper air maps, but we're pretty much focused on wind speed at this level with the jets. So you see, we've got this very deep trough in the Rockies. You've got a strong jet stream coming in off the Pacific. And one thing to note is when you see a trough like this, if you see the stronger winds on the western side of the trough, that means the trough is going to dig or strengthen, perhaps gain that negative tilt that Bryce was talking about. And that's important for us to draw the storms closer to the coast. You have to have that negatively tilted trough. If it's a positive tilt, then the system's going to lift out or move offshore pretty quickly and not have a chance to strengthen. So in this case, this will be a deepening trough. You've got the jet max on the western side. If it's over here, then it's odds favor the trough is going to lift out and weaken and won't promote, big storm development at the surface. So something that we can look at. And within the jet stream, as we've shown in some of the event reviews, your lift is favored in two areas of the jet. It's on this side, which we call the left front quad, and this side, which is the right rear quad. This is where you have divergence, so the air is forced upward. So you have convergence both in this area here. It's called the right rear, or sometimes even the right entrance because the wind is coming in here. And this one is called the left front or the left exit region. So think about the wind is coming in here and exiting out here. So it's this section here where your convergence is maximized. You're getting a lot of lift. And on the opposite side, you're getting downward motion here, and here. So if you can remember that, that's a good rule of thumb. This side of the jet and this side of the jet is where you're going to added lift from divergence. So that's something to look at aloft. All right, so let's talk the forecast process. And Bryce will probably tell you, he's probably sick of me telling this to the staff since I handle the training. But when I was even back in school, 30 years ago, they taught us the forecast funnel method for forecasting. So you start on the really big scale, you work your way down to kind of the smaller scale and the details. So even when we do our weather briefings here, you notice we start with some of the big picture items and kind of work our way down. Well, that's really the forecast funnel approach, it's called. So it focuses, again, hemispheric, synoptic, which is essentially, think scale of the United States, and then mesoscale, which might be a section like the Northeast or the Southeast. Then you can get even smaller, like to Massachusetts on the mesoscale or microscale. So start with the big picture and you work your way down. So let's talk about some of the forecast models or numerical weather prediction. We'll just do a quick kind of overview, and we are planning a Weather Models 101 down the road, so stay tuned for that. But these numerical weather prediction models, they're one source that we draw upon to make a forecast, especially at longer time ranges. What Bryce mentioned talking about trends and persistence, that's good for like the first 6 to 12 hours. But, these numerical models really, really do well, say beyond 12 hours and on out. They use a current analysis as a starting point. So, what we always say is garbage in, garbage out. We want to have a good analysis for the model to begin with. And then it projects that into the future using all sorts of equations of motion, equations simulating what's going on in the atmosphere, very, very complex. And it's just, to me, it's amazing that these models are as good as they are and can really pinpoint weather down to such a small scale. So this is what it looks like. These days we've got these supercomputers down in the DC area, 213 trillion calculations per second, which is just amazing. The technology gets better and better, almost seems every year. And especially there's been leaps and bounds in the past 5 to 10 years in our computing power. But they give us output, like different plots for, say, tropical systems. And you've seen all these kind of what we call spaghetti plots, where you've got different, ensemble members showing different solutions. So that's one some of the output, but there's just all sorts of different output from the models. And, again, they do the math for us. They take initial conditions and come up with its own analysis, which is prone to error, and that's why models are not perfect. They run equations which have, they're all simulations of wind and temperature and moisture and pressure, using all sorts of, different things like the ideal gas law, Newton's second law of motion, hydrostatic law. Bryce, this is bringing back horrible nightmares from college, but really, it's simulating all of these processes, and you have to remember, a little error at the start grows exponentially through a model cycle. So if even there's a little error, maybe in a surface analysis, that can make huge errors in a 2-day forecast. So something to keep in mind. And the models make assumptions. So each model is different. It's designed that way because, let's say, if the GFS was exactly the same as the Euro and exactly the same as the Canadian, you'd have the exact same forecast, which we don't want. So different models use different assumptions, different physics, and different scales too, high resolution, lower resolution, to capture different things going on in the atmosphere. So it's these assumptions that actually lead to errors, and that's why the models are not perfect. So as forecasters, you kind of begin to learn, when is the model good in this situation? When is it not going to be good in this situation? A lot of it is just experience and going from different weather patterns. So, and Bryce can probably tell you, coming from an inland office like Spokane and coming to a coastal office like Boston, there's a lot to learn about the different weather patterns here versus what he had in Spokane. So, but I say, Bryce, you've done a pretty good job picking up pretty quick on the coastal things. So just a few of the models, I'm sure many of you are familiar with these. The global models, these are what forecast on a global scale. So not just North America, United States, but think about the Southern Hemisphere, Australia, Asia. A lot of other countries use our weather data. It's shared freely. But so the GFS is obviously the American global model. forecasts out to 16 days, 13-kilometer resolution horizontally, and 64 vertical levels going up. So think about that 850 millibar to 200 millibar level. Whereas the European model will go out 10 days. It has a higher resolution up to 9 kilometers, also a 16-kilometer lower resolution, and 91 vertical levels. So a little bit different than the GFS, and that's by design. We don't want models being exactly the same. Then we have the Canadian model on the left. That goes out 10 days. It has different resolutions, 84 vertical levels, and the UK Met model, which goes out to 6 days and has its 10-kilometer horizontal resolution. And that just means the grid points are 10 kilometers apart. So the higher the resolution, think 3 kilometers, and I'll get to that in a minute. Those are like your thunderstorm prediction models, whereas these are global models. They do very well with the larger scale weather. Think about our coastal storms and things like that for large scale weather. So here, these are our high res models, and these are primarily run in the United States. And we have the NAM, the North American Mesoscale model, on the left, which is a 12-kilometer model. And it feeds into the one on the right, which is a 3-kilometer model. This 3-kilometer model doesn't have data from all over the country, so it needs the 12-kilometer NAM to kind of get it started and give it that information. So this is what we call nesting kind of in the modeling world. We nest this 3-kilometer grid inside this larger grid that covers more of the actually United States and North America. So you get better forecasts that way down to this 3-kilometer resolution. Hope that makes sense. But anyway, these typically run out shorter in time. You can see 3.5 days for the 12-kilometer, 2.5 days for the 3-kilometer. But these are pretty much designed to capture mesoscale events. And I'm talking about things like snow bands in the wintertime, changing precipitation types, thunderstorms and squall lines in the summertime. So think about more localized weather features. And then we have the model ensembles. We've talked about these. The GFS has 21 different members. And what does that mean? Those are 21 different initializations of the GFS model. So they'll tweak some of the initial conditions. They'll use a different physics package on the model. Pretty much a number of changes are made. And it helps us with uncertainty. So if you start a model with, say a current weather scenario, tweak it a little bit, then you'll get a different output, or tweak it with a different physics package. What it uses to develop thunderstorms, which are called, it's convective scheme. There's different things that the modelers can tweak to give us different output. And you'll see, like in this example here for Hermine, they're very tight in the beginning, but then as time goes on, you can see you get a lot more spread. And it helps us with uncertainty in the forecast. If these are all in agreement, these 21 different members, then our confidence is very high in the outcome that the model is giving us. If there's a lot of spread, like here on the right, that tells us, okay, there's a lot of uncertainty here. We got to be careful in the forecast and not go gung-ho with like the highest amount that we're seeing from the model. We might want to be a little more conservative and tone it back. So as Bryce mentioned about atmospheric soundings, the models actually produce these as forecasts. So this is the model's idea of what the atmospheric profile will look like. So we have an observed sounding on the left and a model sounding on the right. And this also helps fill in the gap between observed soundings. So for us, right now we have Albany and Upton on Long Island and Gray, Maine. But say we want to see what does the sounding look like over Boston or over Providence or over Hartford. Well, the models can help us with that and give us that kind of picture of what the atmosphere will look like. So when a forecaster sets out to predict a specific variable, there's a great deal of observed and model-generated data, as I showed, but none really provide a definitive prediction. So the forecaster has to apply a knowledge of kind of the average climate conditions, local variations, the typical model behavior or model biases, and just kind of their own experience. Gut feelings come into play a lot as how an event is going to unfold. So we know the models are not perfect. So we can interrogate the models too, and there's many ways to do that. A lot of this is available online as well. You can compare the model consistency and timing. Is the next model run similar to the previous? Has it changed a lot? We see that a lot with winter storms. Something looks really good for a big hit here in southern New England, and then all of a sudden the next run takes it a lot farther offshore. we know model biases. For example, with the winter storm, the NAM tends to be the furthest north and west with the track almost consistently, which has something to do with its higher resolution. It can simulate what are called the convective processes going on within the developing low, the coastal low, whereas the GFS has its spacing is farther apart. Its convective scheme is a little bit different. It may not strengthen the storm as quickly. It can't handle that as well. So we know that. We can also monitor trends in the timing and strength of weather systems and check how do the model initialize. And this is something we probably don't do enough of. If we've got say a trough out in the Rockies, which is eventually going to give us a winter storm here on the East Coast, we need to look at the satellite information and see, is that shortwave being analyzed properly? Is it strong enough? Maybe the model isn't strong enough, and that will lead to a downstream issue here on the East Coast. Maybe it's too strong, and it's, amping up a storm, strengthening it too much. So those are things that we need to look at. And that's where hand analysis comes in as well. Very helpful too. See how it compares against the model in reality, and that can help with downstream effects, 2 to 3 days later. So putting it all together, we come up with our forecast. You've seen the area forecast discussions, I'm sure. That gives our forecaster reasoning. Everyone kind of has their own way of writing them. I'm sure you've seen the different forecasters at our office. Some like to write a lot, some don't write much. It's just kind of a personal thing. But we put our piece of the puzzle together here in Southern New England. It goes to a national digital forecast database across the U.S. You have your hourly weather graph information available for your specific area, or point and click forecast here on the right. And of course, we can make nice graphics for the website and for social media too. So always a lot to consider. So let's finish up with some forecasting rules of thumb here as we go on. Just some of the things we've noticed here. They don't all apply to Southern New England, but for the area. So typically the weather is often most volatile in the afternoon. Remember, nights and mornings more likely to be calm, especially during the summer months. We know that. The sun's heating during the day causes the temperature difference between the land and the air. Remember, we talk about lapse rates with thunderstorms. Air and moisture move up and down. We have condensation. We generate what's called convection, big towering cumulus clouds, and eventually thunderstorms. With high pressure or pressure that's rising, its tendency, remember, air is staying put at the land surface, essentially. Think stable weather, fair weather in most cases. If the pressure is falling or we have low pressure, air is moving upward from the land surface into the atmosphere. It indicates changing weather. For those of you with a barometer at home, there's usually a little weather guide on many of them, especially the older ones. And, falling pressure usually means stormy weather coming or unsettled weather coming. For years, that's what mariners used, taking a look at the pressure trends out at sea, knowing if storms are coming. Many rules of thumb from that. When we're forecasting our daytime temperatures, if cloudy skies are expected, obviously you're going to forecast lower temps than you would predict if clear skies were expected. You don't have that sunshine. And on the opposite side, when we're forecasting nighttime temps, if you have cloudy skies, you're going to forecast warmer temps than you predict if it were clear. And we know that the clouds act as a blanket at night, kind of trap that heat near the ground. And often we go colder than our guidance when we have what's called radiational cooling. So clear skies, light winds, kind of a dry air mass, meaning there's a big difference between the temperature and the dew point. That's going to give you those good what are called radiational cooling nights, where you typically go lower than a lot of the guidance would suggest. And areas of high pressure, if you're to the west of the high pressure center, you're going to be warmer because you're in that what's called return southwest flow. And if we're on the east side, we get a colder north or northwest flow. I think we've seen quite a bit of that this fall, where a high pressure moves in from the Great Lakes, and we have a couple of days of chilly weather, maybe even this past week, some frost early in the morning. And now this later in the week, the high's moving offshore. We're in that warmer southwest flow, and actually pretty mild here for the middle and end of the week. So something else, and we talked about this in our perfect storm review, there's actually a neat little trick you can do on a weather map. So take the difference in pressure, and this is in millibars, between the high pressure to the north and your low pressure itself. And that'll give you an estimate of the wind gust potential in knots. So in this case, for the perfect storm, this was during its life cycle, not at its peak. the high pressure to the north was 1,044 millibars, or a 1044 high, we'd call it. The low at that point was 983 millibars. So what's the difference? It's 61 millibars, which would roughly equate to a gust of about 61 knots during that time frame. And that was pretty much ballpark. Gusts were in about 60 to 65 knot range at that time. So we use this a lot during the winter time when we have the strong high pressure system to the north and these deepening coastal lows off to our south. So give it a try this winter, see if it works. It can be a forecast, and try and get the lowest pressure or the time when the storm is at its deepest to get that biggest difference and see if it works out. It usually works out pretty well. So some other rules of thumb: when snow cover is present, you forecast lower daytime temperatures, and at night, snow on the ground gives off heat, so causes rapid cooling. So we forecast lows to be lower than we would if there was no snow cover. It kind of chills that very lowest layer, as you can see here near the ground. So daytime temperatures tend to be a little bit colder despite bright sunshine, and especially at night, it can get pretty cold with that snow cover. And then, as I mentioned, on a calm night, temperatures will be colder than on a windy night. Since you're not mixing, you're allowing that heat to escape right up into the atmosphere. So that is, I believe, it, Bryce. And I know we've probably gone a little bit longer than we do for most of our webinars, but do we want to go through any questions here? Appreciate everybody hanging on. We will do a weather briefing in a few minutes. Bryce, are there any questions in particular that we want to mention?
Yeah, there's a couple of good ones, so I'll go through them
All right,
here.
Go ahead.
All right. So first one was, why is it called a Rex block? And that is a great question, because I talked about how the Omega block was because of the shape. Rex block is named after the meteorologist who identified that shape. So this was Daniel F. Rex, who identified that in 1950. So that's why it's called the Rex block.
There you go. Great question, John.
I learned
All right.
that today. I learned that just now, so that's great. I learned something.
There you go.
How do you know or examine the shortwave strength with satellite imagery?
So yeah, that's a good question, Brian. So you want to look for you'll notice dry air. You'll notice a sharpness to it. And the sharper it appears, you'll see that little dip in the satellite image. You want to use water vapor imagery, I should mention. Typically, that will show it the best and at the highest level. The GOES 16 gives us high level, mid level, and low level moisture. You really want to look at the high level because that's where we're sampling. So you want to look for a good contrast between those, the brightness or the moisture between some of the drier air, almost is like an orangey kind of color. The tighter that gradient, usually the stronger the shortwave. And we in our office, we have the AWIP system that you see there on the top middle image. We can overlay the model forecast onto the satellite picture. So it really helps us compare what the model is doing with what's happening. But you can also, just kind of put the two side by side, maybe in a couple of windows, on your PC, and kind of look. So look for those tight gradients, I would say, most often. That will tell you a stronger shortwave. Whereas if it's a little more dispersed or not quite so organized, you can kind of tell that it's maybe not as strong as what the model might be showing. But good question. It's best if you can overlay it. I think actually, Bryce, maybe the Plymouth State site, you can do that. I'm not sure.
I think you might be right about that.
Yeah, there are some of the websites out there where you can actually do that yourself. So hunt around, do a good online search, and I'm sure you can find that. But great question.
This one is about the troughs I mentioned. So is there a reason why negatively tilted troughs are more significant as far as severe weather producers? And yeah, that's a couple of things, mainly because with that configuration, you have the surge of warm air coming in underneath the incoming cold air above it, and that creates instability. And then also it's a good configuration for good wind shear. So there's a big change in wind direction from the surface into the upper atmosphere, and that wind shear is what helps to sustain storms to become stronger. So those are the main kind of factors at play, and why negatively tilted troughs are typically more prone to produce the worst storms. Good question.
We actually, I'm sorry, we have one from Jeff here. He was talking about, I know you rely more on the Euro in the winter. Where do you find that information? That's actually a pretty timely question, because Previously, they actually did not share all the data freely. They would with our friends at NCEP down in DC, but even at our office, we only get a subset of the European data. But now they're actually make it more freely available. And I put it in the chat. I answered well, you have to look at the question, but I'll put it in the chat too. Their site is ECMWF, so it's ECMWF.int. So if you go to that website, you'll actually find a lot of the European model data there now. It's all freely available. But I would also caution you, I know everyone says Euro is king, Euro is king. Be careful. There's not one magic model that does everything right. The Euro is no doubt a good model. I will tell you, it does not get every storm right. It actually struggled mightily this past tropical season. The GFS outperformed it. So look at it, absolutely. Do we put confidence in it? Yes, but it's only one of many different models. So don't just, please, if I teach you nothing else tonight in class, do not rely on one model or one model run. Look at probabilistic data, ensembles. Maybe we can do a class on ensembles, Bryce, next. Look at the different model solutions. Look at model trends. Don't just lock in and say, well, I'm going to look at the Euro at this run and the next run. And don't do that. Look at and understand the model is a tool. It's not going to give you necessarily the answer. So our professors used to tell us, use your brain. You're trained as a meteorologist. I know a lot of you know a lot with forecasting because you do it day in and day out too. So use your brain, use the model as a tool in the forecast process, not as the final answer. I know we've got a lot of neat graphics like snowfall maps and everything, but we probably need to do something on snowfall maps too in our model class because those are prone to a lot of error. So just a caution there, but definitely that ECMWF site is got a lot of good free information that you can use. So go ahead and use it. Bryce, I'm sorry I interrupted you.
Oh no, you're fine. It looks we probably got time for one more question. It's 8 on the dot. So let's do with this one. Do jet maxes play into winter weather in the U.S. and how are they different from spring severe weather? What level is the jet max located at?
Yeah, so winter weather, there are two levels you want to look at. So you want to look at, as I mentioned, that 200 to 300 millibar layer. You want to look at the upper jet, it's called. And that's where you want to find that left front quad or the right rear quad. Remember, I showed those two areas on the jet max. Those are areas where you're going to get added lift. So think about you get a little bit of an extra oomph or a little extra bump of lift, and you want that. Now, you also want to look at the lower level, 850 millibar jet. Now, if you've got, and it's a similar thing, left front quad, right rear quad. Sometimes in big winter storms, we get what are called coupled jets. So you'll be in, say, the right rear quad of the 200 millibar jet and the left front quad of the 850 millibar jet over the same area, and that's giving you gobs and gobs of extra lift. So that's going to be really favorable for heavy snow in the winter or heavy rain if it's a rain event. So look for those coupled jets in the wintertime. It also works in the summertime too, for severe weather. Those are areas where severe weather is favored. Again, left front quad or right rear quad of that jet max, both 250 millibars and 850 millibars. So if it's coupled together, just like I mentioned, then you've got kind of an added enhancement that's really going to help you out, whether it's rain or snow or severe weather.
All right. Sounds good. So I think we are